All right, so I'm going to tell you a little bit about the new BilboMD web app that I've been working on recently. So I think you've all sort of been introduced to BilboMD at this point, but I would just give you a brief introduction, like what is BilboMD? Essentially, it is a computational algorithm for generating a set of models consistent with SACS data, right? So as we all know, because we're here in a SACS workshop, macromolecules are flexible. To use BilboMD, what you need to do is define the domains and the parts of your protein that you think are rigid, which ones are flexible, and then BilboMD will generate an ensemble of models representing possible conformations and then check them against the experimental data. So, you'll generate your initial model either from experiment if you're doing crystallography or cryo-EM or NMR or something like that, or you can generate a hypothetical model using AlphaFold or RosettaFold. And then using CHARM, which is a molecular dynamics package from Harvard, or originally developed at Harvard, this will do energy minimization of your model, heat it up to 1500K, and then go through a production phase using distance and RG restraints in order to generate tens of thousands of models that may represent what your protein looks like. And then we go through SACS validation, where we take those calculated models and calculate theoretical scattering profiles from them using Fox, which Susan had talked about. And then using multi-Fox, you can go through those calculated scattering profiles and find like an ensemble of those that fits your data the best. And so the inputs to BilboMD are your initial model, your SACS data, and then a user-defined rigid and flexible regions of your model. And I put an asterisk by that because the new features that we've begun to introduce, Mikkel and myself, are starting to make this a little bit more automagical. And then what is output from BilboMD are from one to a few new models that best match your experimental data. And this was introduced really nicely earlier by Bettina, who I'm sure is probably in bed by now. She gave some really nice examples of how she used BilboMD with her protein. And her protein was not just a simple protein. It had had post-transcriptional modifications. It had large heme ligands, and it had mobile domains, which would adopt different conformations based on different pHs. So this is like a real ideal type of a system that can be addressed with BilboMD. So I'm just going to throw this slide up here because this talk is being recorded, and perhaps these slides will be available somewhere for download. Just put those references up there right off the bat so you can know where to go read a little bit more in detail about what is going on behind the scenes with BilboMD. And that's that top reference that I've highlighted in green. But BilboMD does make use of Fox and multi-Fox. So those next two publications highlight those applications. And then CHARM, if you want to, CHARM is an incredibly powerful program, and it's used for all kinds of stuff. So that's the reference for that down there at the bottom. So the original BilboMD, we'll call this BilboMD, the OG. This essentially was a Perl script written by Mikkel Hamel back when he was, I guess, a graduate student, or maybe early in his postdoc, he was still working on that. And then there's this front-end web app that was written by Kevin Dyer and myself. And so this runs on Stomp, which is an old machine in our server room. And it sort of just has not been updated in the last 10 years. The URLs there up at the top if you want to visit the BilboMD website and submit a job. So it runs on Apache Tomcat, uses JavaScript. The actual running of all of the Fox, multi-Fox, and CHARM is done through a Perl script. And then there's like a job submission system sort of to queue people's jobs up so that the first job submitted is the first job run. So there isn't a huge amount of computational capacity. So if a bunch of people submit jobs at once, things will pile up a little bit, but eventually they will run. So the limitations for this BilboMD, the OG, are a little bit numerous. I mean, it is only really able to take protein. No DNA, no new RNA, no post-transcriptional modifications, no ligands. It uses a relatively old version of charm, which is still valid. It's just there have been some improvements to charm over the years. It sends the results as a link in an email. There's no ability for the user to see their job history. Even though there's a check your jobs button up here, it doesn't work. Has poor error handling and reporting. There's no admin tools. There's no persistence of your jobs. There's no database. It only runs on old, outdated operating system. Not easy to update, essentially impossible to update. The one good thing about it is that it takes regular old PDB files. So it does, even though it's running charm, you can submit a regular PDB file, and Mikkel's Perl script will convert that into a form that is compatible with charm. So you're like, okay, well, how did Bettina use this? If you can't put post-transcriptional modifications and ligands into here, how is she using BilboMD? And essentially, over the years, Mikkel has sort of developed BilboMD 2, which is essentially a standalone Perl script that just runs on the machines at the Beamline here. And it uses a newer version of charm. And instead of taking PDB files, it takes CRD and PSF files. These are charm-specific input files. So essentially, you need to convert your PDB file into a CRD or PSF file to have it run. And this BilboMD 2 is able to, with the proper restraints and other files, is able to handle pretty much anything. So the challenge for me was to take this new script from Mikkel, or at least take the logic behind his script and turn it into something that's generally usable by everybody on the web. Like, you don't need to SSH into our machines and run this Perl script, or you don't need to ask Mikkel. You'll just be able to come and use this new BilboMD. So this is the sort of the flow of the script. The user inputs are put in at the top. This is your PDB file, your data, definitions of rigid and flexible domains, and your run parameters. Charm does a minimization and a heating step, and then it will run some parallel molecular dynamics runs spaced between what an RG min and an RG max that you define. And then within each of these molecular dynamics runs, it's run several times. Each one is outputting a trajectory file. And from these trajectory files, we extract PDBs, 200 PDBs per trajectory. And these are put into Fox to calculate theoretical profiles. All of these theoretical profiles are then dumped into multi-Fox, and multi-Fox outputs its guess as to the best arrangement of, or the best ensemble of models that matches your data. So in writing this new BilboMD, my goals were to sort of rewrite it from the ground up. Use modern web technologies, make the code portable, make it editable, make the code scalable, and improve resiliency. So if the code that is actually running the charm module goes down, jobs will pause, and when things become available again, then they'll continue to run. I wanted to separate the code into logical concerns. It was, and I don't think Mikkel would mind if I said this, but Mikkel's code was just one giant function from top to bottom that just did everything, and it was not easy to see what was going on. He had a script that wrote a script that wrote a charm script. So it was like very, very Russian doll-like, stuff inside of stuff inside of stuff. So want to refactor this, improve the layout and the organization of the code, improve the user experience. I didn't want to have to deal with passwords because nobody ever remembers their passwords, and I didn't want to deal with passwords resets and all this kind of stuff. So all you need in order to use the new BilboMD is your email. And it's going to be able to handle nucleic acids, post-transcriptional modifications, and hopefully most ligands, but that's still, something that needs to be tested. Because of the way the code's been organized, it opens up the possibility for adding new features. It's much easier to adapt it. And so we're using GitHub for the development. And so, although this isn't necessarily of interest to people here, I'm going to point it out anyways, because this was a big effort on my behalf, and it only takes a slide here. So this is how I've organized the new BilboMD. The front end is this gray box up at the top, and that's what we're going to concern ourselves with for the rest of my talk, which is the UI. This is the web-based UI. but it's written in React. This is a new, relatively modern JavaScript framework. It uses Redux, Material UI. This is a Google library of like buttons, text entry boxes, things like that. I didn't want to have to reinvent forms, so I'm using a package called Form. And then we want to make sure that what people are uploading to the server is valid PSF files or CRD files or SACS data. So we use lots of front-end validation. And then on the back end, everything has been Dockerized so that it can be moved around from machine to machine very easily. Okay, so I'm not going to belabor this too much other than to say for the rest of the talk, I'm just going to talk about the UI and sort of some of the underlying logic that's gone into the actual BilboMD script itself. So when you log into the new BilboMD, you'll get this really sort of basic looking dashboard. I picked a very exciting gray color for this web app. And from your dashboard, you'll have access to sort of 4 areas, 4 links. One where you click on that, it'll show you your jobs. Here's where you can start a new BilboMD job. And then I have these 2 jiffies, or as Mikkel calls them, yiffies. So we have our INP yiffy and our PAE yiffy. And these are used, I'll explain these in a second. When you go to the new job tab, there are some instructions right at the top on what inputs you need. Now, this new BilboMD is different from the BilboMD OG because it does not take PDB files. You need to convert your PDB files to charm coordinate files and a charm data structure file. And so the way you do this is you go to the Charm GUI website and you make an account there and you use a little thing called PDB Reader, and that will allow you to convert your PDB file into a CRD and a PSF file. And then this INP file.
Scott,
yes.
Can I ask you a stupid question?
No, only intelligent questions allowed here. Go ahead.
Why not just have people input their PDB and then have it automatically convert to a CRD or PSF file?
Because the code that's used to convert from a PDB to a charm compatible coordinate file is not open source.
I see.
So the lab that has developed this charm GUI is a little bit whatever. So
okay.
Their code is not on GitHub. I cannot just go there and get it. And it is possible we could write our own converter, but that's not a priority at the moment since someone has already done it. So it's a little bit of a detour that you need to make in order to use this, but it's really not too big of a speed bump, I hope. Okay,
thank you.
Yep, and then you need, and this is, I'll talk about this more later, you need an INP file. This is a charm formatted input file that defines the rigid and flexible regions of your protein. And then you need your SACS data, a 3-column SACS data file, which I guess has whatever, I don't know what the hell it has in it. It's got like angle and R intensity and error. Okay, I am not a SACS person. Okay, so this is the Charm GUI, or this is the homepage for it. Once you log in, this input generator is the thing that you want to use. I'm not going to go through here and show you how to use it. I'm just showing you the web page. This is where you would go. And it's hosted by a lab at Lehigh University, and they don't want to share their code. So, all right. So once you hit the little disclosure triangle, that will fold up the instructions and leave you with your form. So you put a title here. You upload your CRD file, your PSF file, your const.inp file. It does not need to be named const.inp. You can name it whatever you want. I think it has to end in .inp, but I think you can name it whatever you want. If you don't have a const.inp file, you click on this little green button, and I'll explain what that does in a second. Here you select your SACS data, and then these RGmin and RGmax, these are the values that are going to be supplied to the molecular dynamics runs in order to limit, kind of give charm some sort of constraints on this, how much it's allowing the various flexible domains to move around. And then the confirmations per RG is just the extent and the number of models that are generated. And when you're just sort of testing things, you might want to pick, there's only 4 values, 200, 400, 600, or 800. So if you want it to go quickly, pick 200. If you're wanting to go exhaustive and explore as many confirmation as possible, then pick 800. Once you okay, and then once you hit your submit job, your job will be submitted. And if you now go to the My Jobs tab, you'll just see a summary of your jobs, the title, the date you submitted it, your username, and then the status. It'll tell you whether it's pending, it's running, it's completed, or if it's in an error state. If you click on the little information button here, it will take you to an information page, which at the moment is pretty sparse. It doesn't have a lot in here other than your title and the status, a summary of the inputs that you put into it, and some ID numbers, which come in useful. If you have an error or if you need to ask me any questions, this is how you should refer to your data. And then if it's done running, then there'll be a button here for downloading your data. So once the job is completed, it will say completed. And now when you click on the information button, you will now get a download results button. If you click on that, you'll get a tarball, so a .tgz file, which if you uncompress it, it will have a bunch of stuff in there. I'm not going to explain it to you. Go talk to Greg, Mikkel, or Susan if you want to know all the information, all the stuff that's in there. Now these are the 2 YIFIs. We have the INP YIFI, which you can use to manually create a const INP file. And then I just added this week this new one, which uses the PAE errors from AlphaFold 2. It also does use the LDT values too. So if you click on this INP Jiffy, and I'll demonstrate these ones a little more towards the end of the presentation, but this one will allow you upload your CRD file, the same one that you plan to use for the BilboMD run, and it will validate the domains in there and allow you to select which chain and what residue range you want to define for each rigid domain. So the idea is that you can have rigid bodies, and the rigid bodies are contained of rigid domains, and the rigid domains are connected by flexible bits. But you can have more than one rigid body. And the first rigid body, your primary rigid body, will stay completely fixed. But if you add a second rigid body, it can move around in relation to the first rigid body. But within each rigid body, you can have, it's just like a hierarchical organization of the rigid and flexible regions. And this Jiffy, I implemented pretty robust validation. So as far as I've been able to test so far, the INP files that are produced by this are all valid charm input, and you should not run into any problems, but you might. Anyways, I'll demonstrate this in a second. This is sort of what they end up looking like. There's some links in the instructions on this format. So this is charm atom selection syntax. And so this is sort of an example. And so if you know a lot about your system and you feel very comfortable defining the rigid and flexible parts yourself, then you should use this manual tool, right? So, but this takes intuition, domain-specific knowledge, guesswork, and there's a lot of other tools out there for sort of predicting intrinsically disordered regions. I mean, there's tons and tons of stuff out there. So that is if you want to do manually. But AlphaFold provides us with a couple of very useful tools. I mean, other than the 3D predicted structure, which is like what most people are interested in getting when they run AlphaFold 2, it does write these confidence scores into the B factor column of the PDB or MMSIF file. And so these are sort of an estimate of the local goodness of the model at that particular position. It doesn't give you a sense of whether the global fold is okay, but are the residues in this alpha helix or beta sheet, are they sensible and do they make sense? And so you can see this picture here is sort of colored based on PLDDT. So you see areas that are in blue have very high confidence. So it's these little kind of globular domains, AlphaFold 2 seems to be predicting very well. These longer connecting regions have very low PDDs, less than 50, and can sort of be inferred to be flexible. The other thing that AlphaFold 2 gives us is this predicted aligned error plots, which kind of look like this. And in older versions, these were as a pickle file, but in newer versions, these get output as a JSON file. So I actually want to just head over here for a second. I'm going to show you two things. I want to show you this web app called a PAE viewer, and then I want to quickly show you that Chimera X can do the same thing. So this PAE viewer paper came out just this past summer, and it describes a nice web server for interactively visualizing these plots. And so this is the website. It's linked right from the abstract of their paper there. And I'm going to go to our upload, and I'm going to upload this PDB file, which is a DNA repair protein. I think this is XRCC2, I think. So that's the PDB file. And I got this from the AlphaFold database. So it came with a PAE JSON file. So you select those two. And this website was made to visualize cross-linking data, but it's optional. You don't need to do that. If you just upload a PDB file and a PAE plot, there you go, you'll get that guy. And if you model it by confidence, and then it's showing you the PAE plot here. And so if you're not familiar with these, the lower the value, the more confident AlphaFold 2 is that these residues are, it's an error where you're aligning every residue in the structure against every other residue in the structure. And so it will, highlighting this area here, you can see that it's defining a domain there. If you highlight along the diagonal this other dark area, you can see it's defining that domain. And if you get this one down at the end, you get that one. And there's like a little one right here, which is this little helix. And now the interesting, so this sort of allows you to define, okay, we have domains look like this, flexible linkers look like this, where it's just a diagonal and a little bit of dark area along the diagonal. But these areas that are in the off diagonals, if you highlight them, will show you that AlphaFold 2 is predicting that there is likely an interaction between this domain and this helix. And you can see that on both sides of the diagonal. So this PAE plot, if we could figure out how to parse it, would give us information about, one, what are the rigid domains? So we would anticipate these things to be rigid domains. And possibly this one, this little domain here would be interacting with this domain here. So we might want to put that domain defined by the blue and this little helix defined by the orange. We might want to put those in the same rigid body, okay? But they would be connected by a flexible linker right here. So the challenge here is to take this, this data, this PAE data, and use it usefully to create an input file. Okay, but first I just wanted to show you, for those of you that use Chimera, if you go to Chimera, and I'm gonna open that PDB file, that same PDB one I uploaded. And then you go to Tools, Structure Prediction, AlphaFold Error Plot. And I've already opened it, so it's selecting it right here. But you could browse, find your PAE file, and now it will open that same plot that we saw on the web browser. And you can, again, highlight areas that look like they might be domains, and it'll color them in the viewer here. And you can see these off diagonals also show up here. The thing that Chimera does, which is kind of cool, it has this color by PAE domains. And if you click on this, it's doing some sort of magic behind the scenes to automatically like parse what is a domain. Although it is sort of lumping together the flexible stuff with the rigid stuff. So, but this gave Mikkel and I a clue that there was something being used in UCSF Chimera that we might be able to take advantage of. And it turns out that there is, and we did. So that's how I found out about, here, let's go back to the presentation. Yeah, I'm not gonna read that. I pretty much explained that to you. You can pause the video and read that if you want. So the challenge is that the PAE data, this is what it looks like. I mean, it's a giant matrix of matrices with these integers in them from 0 to 37. And we needed a way in a script to parse this data out of here and turn it into, hey, residues 35 to 400 is a domain, and residues 400 to 450 is a loop. And so this is math to the rescue, right? So this is what I was alluding to when I asked LJ about possibly investigating graph theory to look at the communities in the SAC similarity matrices. So there's been some work on this lately, and a very interesting algorithm has recently been developed called the Leiden community algorithm. And this is used by Tristan. Tristan he wrote this program called, I'm not even going to try to pronounce. Okay, I'll try to pronounce it. I think it's Isolde. Anyways, go look that up on the internet, see if you can figure that out. Anyways, he had a little Python, a little bit of Python code in his Isolde source code that uses a Python package called iGraph, and in particular uses this Leiden community clustering algorithm to find the clusters within a PAE graph. So we adapted this Python code to our nefarious uses, and we've implemented it as this PAE Jiffy. So this PAE Jiffy is right below the manual one. And this one takes just the CRD file and your JSON file that has your PAE data in it. And so it takes a predicted align error representing the predicted error and distances between each pair of residues in a model, uses this graph-based community clustering to partition the model into approximately rigid groups. But it kind of just, it clusters a lot of the very low PLDDT areas into the rigid group. So we are also using PLDDT values to discriminate whether a community should be treated as a rigid community or a flexible community. And then, yes, and so our Python script was inspired by Chimera X and the plugin by Tristan Kroll. And so I just put that up a couple days ago. Feel free to try it out. Mikkel's tried it with a few of his sort of test cases and it seems to work. But I'm just going to say that that's experimental at the moment. Okay, so I'm at half an hour almost. I just am going to give you a real brief tour of BilboMD. So, okay, so I'm logged in as a regular user here called Classen. If you click on the main dashboard, you'll get a little bit of information about papers to reference and links to Charm GUI, Fox, and Multifox, and the associated publications that describe those. And then links to AlphaFold, iGraph, and NumPy, which we use in this application. And so this is my job. Let me make this bigger. There we go. So this is the My Jobs page. You can delete your job there. You can look at information about your job. You can download the results here. There's no, at the moment, it's fairly new. There's no visualization. There's no little molecular viewers. There's no colorful plots. It's just, you upload your files, we run awesome BilboMD logic on it, and you can download your results. There's definitely room for improvement, but we wanted to get this thing up and running as soon as possible. So there are the instructions. This is the form for submitting a new job. This is the input Jiffy. I'll come back. Actually, let's do this. So there's some instructions up here. Tells you that you need a CRD file. So let's see what that one looks like. Yeah, this is boring. It only has one protein. Let's try whatever. It's fine. So it'll just parse your CRD file and tell you how many chains you have, how many residues, first number, last number. Click the next. But then we'll set you up with a default rigid body with a single rigid domain in it. But say you're like, oh, I know that this is going to have a chain that starts at 67 and goes to 134. Now it's already telling you that you can't have overlap in here. So you need to, this needs to be maybe 63. So as long as you, anything that you define in these light blue boxes will be rigid. Anything that's not in there is assumed to be flexible and will be allowed to be moved around. If you're like, okay, these two domains are this, imagine this is that little helix and this is that little rigid domain it's attached to, but I want to have another rigid body that will move independently. And that one starts at 200 and goes to 300. Okay, and so if you're like, and then it'll summarize, you have this rigid one, rigid two, and then within your this rigid body, you have another rigid thing, and you're happy with this. Then you go to next. It will give you a summary of what your const INP file will look like. And you can either just copy it to your clipboard and paste it into a file, or you can download it if you want to just download it. Okay, so that is the manual one. The one for PAE is even easier. You just select CRD file. So there's my molecule in CRD format. Here's my PAE data in JSON format, and you submit it. And okay, this is pretty ugly here. Granted, I just, it doesn't, I haven't put a preview here with a copy to mouse buffer or to clipboard. So I'll do that. At the moment, you just have to download it. So there, download, and you're done. So that is the BilboMD app as it is right now. And I think that's, let me just jump back here for a second. So I have some ideas for future development. And so a lot of these are just for my own wants and needs, not necessarily scientific wants and needs. Better logging. It'd be nice to have the user edit or delete their own account. The job detail page does need, it needs to be improved. And maybe a molecular viewer allowing you to see the models that were generated by BilboMD. Perhaps the ability to edit and resubmit a job without having to upload the files. Like maybe, hey, I just want to change the RG min and RG max. Or, hey, I want to run these same things, but with a different SACS data set. For my own sanity, implement better testing. Just people can when you make a public web app, bad things can happen. One of the biggest questions we get is what values should I pick for RG min and RG max? And I think that, I'm not sure that we should really, users should be able to specify those if they want, but we should implement auto RG so that a sensible starting and ending or minimum and maximum RG value would be automatically calculated from your SACS data that you upload. And perhaps just implement this PAE logic directly into new job execution, like rather than having a separate little Jiffy where you have to generate a const INP file, download that file and then re-upload it for a new job. And then test it with a variety of ligands, which I'm sure there are ligands out there that our charm does not know about. Because we're limited in the amount of sort of molecular descriptors that we load into each charm simulation. So we may be missing your favorite ligand. If things error out, if you run a job and you get an error, let me know. And we'll figure out why that is. It might have something to do with your molecule. Okay, so thanks to the Department of Energy and the National Institutes of Health, we get our money from IDAT and ALS Enable and SBDR. And I guess now Task Force 5. And with that, I'll end. Thank you.
I will unmute and bark at people to ask questions. Questions? Things people want to see. Let's see here. Questions. Let's see.
The one thing is, so this BilboMD is not running on a supercomputer. It's running on limited computational resources at the Beamline. So right now, I've limited it to 2 runs at a time. So just be patient. If you submit a job and it just says submitted or running, if it says submitted or pending, I forget which status, just have patience. It will eventually get run. if you get an error, then let me know, because that means something went wrong. But if you go to your My Jobs and this is either says pending or submitted, then just relax. If it says error, then contact me. Yeah. Go ahead, Susan.
Do you think that you'll implement it where somebody can put in an amino acid sequence? And then it'll go to AlphaFold 2 for prediction and, you know,
I mean, we could. But I mean, I'm not sure if people would want that. Like, I would think that people who have SACS data, they kind of probably maybe want a little more control over what their starting model is. Maybe not. I don't know. You tell me. I don't collect SACS data. Would that be useful to you? Like you
No,
would rather, like you'd put in a amino acid sequence and SACS data and just say go.
Yes, that'd be useful.
Oh, okay. Well, I don't think that would be super difficult.
and then the other thing which would challenge the computational thing is that it runs like the 5 different models. So you know how AlphaFold 2 outputs 5 models.
Right. So, I mean, I would just probably, as a first approximation, take the top model, run that through the PAE domain finding code, and then take that along with your SACS data and throw it into BilboMD.
Because we had a situation where model 4 suggested something similar to the helix binding to your domain, and then we tested it and it looks like that is indeed the case, but we wouldn't have realized it without model 4.
I see. Yeah, no, I would like to hear about like ideas like that. I think that's because I don't want to just go coding off of the whims of Susan. If other right, but if that's something that, yeah.
Any of our users,
So-
if you guys have, would you guys have any input on that? For example, would you
Scott,
like,
I have a question.
Scott, you've got a question?
Scott,
Yeah.
this is
Go ahead.
Bob here. It's a good talk. So I have a question. In the old BilboMD, they used to give like a 4 or 5 models and we used to pick it. But here in the new BilboMD, they are giving at least like a 50 or 100 structures. I don't know.
Okay, that could be. Are you getting too many models?
Yeah, and
Yeah.
I don't know which one to pick. Like
Okay,
they're giving
yeah.
models
So
in every RG.
Yeah. That is an aspect of this that I've sort of neglected. So right. I think I need to revisit that bit of code. I think I did not. I asked Mikkel what logic I should use for returning PDB files to the user, and I don't think I followed up, or he gave me a confusing answer. So I just included everything and left it to you to figure out. But that's, yeah, I'll write that. I'll revisit that because I agree. Like, let's see, if I go here and let's look at one of these things. If I download this results file and I come here, that one, yeah, like this one, for example, it gives you back whatever your const IMP file. This one has from RG30 up to RG50, and it's giving multiple models for each one. And I honestly don't exactly know how to interpret these. This is like a Mikkel thing. Yeah. So what I have to do on the back end is I need to interpret these ensemble _size_ files and decide which of these PDB files to send back to the user. And I don't think I am doing that very well. So that's good advice. Thank you. Yeah.
One way to do that, of course, is you can take this set of PDB files zip them up and dump them into Fox and your SAX profile, and it'll do the minimal ensemble search.
But that's what it's doing. That's what we're doing.
I know, but I'm just saying to make sure that Bob isn't confused. I think because like you said, those TXT files are hard to interpret. They have that information, the correct one, like that ensemble size of 2 is saying these are the 2 best ones, and they're in there, the top
Those
2.
two. Yeah, right. Or the other thing that I've been meaning to add is every results file should have a README file in it with instructions. I think that used to be in the original BilboMD. I think there was a README file in there that said, "Hey, look at one of these files, and you can tell based on, well, I don't know, somehow interpreting these ensemble size files, which of these PDBs is the one you want to use." So in this case, it would be the RG34 run 1 27,500, and that one is 88% of the ensemble, and this other one's 11.5%, like that, something like that. I think that's how you interpret it. And the next best choice would be these two here, and this one is 68% of your ensemble, and this one's 33%. I think that's how you read them. But then there's these other numbers in here, which I don't remember what they are, and this one out here, I don't know what those are. These numbers here, I don't know what those are. And those numbers there, I don't know what those are, or that number there.
There's a chi-square, and there's. So, but the for now, until things are fixed, Fox will give you a clear answer. Multi-Fox will give you a clear answer.
This is the output from multi-Fox.
I'm saying the web version will give you a picture of your PDB.
Oh, I see. Right. Okay.
Data, how it looks, and the quality of the fit, and
okay.
So, intuitively output rather than this.
Right. Okay.
Giovanna mentioned an email alert once your job is done.
Yes, that does happen. It's supposed to happen. You should, when your job is done, it should send you an email. And right now, if you go up to your accounts here, there's nothing here, but eventually you cannot edit your account information. If you don't like your username, let me know, I'll change it for you. And then there's a logout button. So really, it's pretty simple at the moment. I sort of just focusing my efforts on getting everything organized in a way that we could add new features easily. And I think I've accomplished that. And so the idea here, like with Docker, is that at the moment I have these little workers fired up, and I have 2 of them. So 2 little workers that run Fox, multi-Fox, and Charm. And each one of them, they look to a queuing system to see if there's any jobs that they should be doing. And when they see a job that's there, they'll grab it and do the work and then send the email to the user. So if we wanted to implement a mode where we would be running AlphaFold for people, we would implement one of these little Docker containers on our machine that has GPUs, so that we would be running the AlphaFold stuff on separate machine, and that would still talk to this same queuing system. So the cool thing about this architecture is you can distribute all of the little components across different computers, and they will talk to one another and coordinate their work. And they don't really care what's happening at the hardware level. If a computer dies, it's very easy for me to get this up and running on another computer. That was actually the original impetus for me rewriting this code, is that the old BilboMD, well, other than not taking nucleic acids and post-transcriptional modifications, it just would only run on one computer.